Good morning, everyone. Welcome to our latest Full Steam Ahead webinar. Thank you for joining us. If we haven't met before, I'm Brian Schmidt, the librarian industry analyst here at Geothermal Rising, and I'm excited to be your moderator today. We have some amazing speakers, but before I introduce them, I have a few announcements to mention. I want to let you know that we're recording this event and it will be available on our YouTube channel within the next few days. And we want to thank all of our members. Your membership helps us continue our mission to build and strengthen the geothermal industry, and we appreciate it. Share my screen. Slideshow. There we go. Okay. So we would like to thank all of our members, our Earth and Energy Visionaries, Baker Hughes, Calpine, Ever, Exceed, Quays, SLB, Turboden, and Egg Geo. We also want to thank our geothermal champions, BHE, Chevron, Fervo, Expro, COSO Operating Company, and Burns McDonnell. And our clean energy enthusiasts, DTEC Geologica, Central Washington University, NREL, Belaruc, Imperial County, Zanskar, Baseload Capital, XGS, and Amorisco. We have a couple upcoming events to share. We've got the Indigenous Geothermal Symposium, October 24th and 25th in Reno, Nevada. Geothermal Discovery Day, October 26th in Reno. And then the Geothermal Rising Conference is October 26th through 29th in Reno. We have the 2026 Geothermal Investment Forum and Oil and Gas Mutual Challenges and Opportunities, April 7th and 8th in Houston, and Capitol Hill Day, April 28th and 30th in Washington, D.C. And we'll have a brief Q&A session after the presentation. Please feel free to ask your questions at any time using the Q&A function in the Zoom UI. And let's introduce our first speaker, Jana Simo. Jana is the Geothermal Portfolio Manager at PNNL. She has a PhD in geology and works across subsurface science with a focus on characterization and modeling. She's going to introduce us to the subject by giving us a brief overview of geothermal research at PNNL.
All right. Good morning, everyone. Brian, we got everything going well here?
Looks good, yeah.
Okay, great. Good morning, everyone. PNNL is really happy to be here to share a little bit about what is going on in our geothermal research at the National Lab. So I will kick this off and then I will hand it off to three different researchers who will do a little bit of a dive into some of the research that we are doing at PNNL in geothermal. So PNNL is a national lab. We are a DOE Office of Science lab. And so our mission is to serve DOE's mission in science, energy, environment, and national security. And we do this by addressing these challenges through transformative science and technology solutions. We're one of 17 national labs. We are located up here in the Pacific Northwest. Our main campus is in Tri-Cities, Richland, Pasco area. Close to Walla Walla. A picture of our main campus is down here in the lower left, but we also have offices in Seattle, which is where I'm based, as well as Squin and Portland. So like I said, we're one of 17 national labs, and each one of the labs have their own unique capabilities, as well as overlapping capabilities with different areas of focus. And this is really important because this creates a really, really strong network working for the Department of Energy and other departments where we form really strong collaborations. And these collaborations and partnering are really critical for our mission success. And it's not just the collaboration between the national labs, but it's also how we together partner with industry, academia, and the community in order to really address those critical challenges in energy and environment. So go a little bit into geothermal at PNNL. PNNL has a long history in subsurface science, and this started off in the mid-60s with the Hanford site and nuclear waste remediation. Fast forward a little bit and getting into expanding our subsurface portfolio into carbon sequestration and actually obtaining the first Class 6 well permit for injection. And then what I want to highlight here is our involvement in EGS Collab. And that's really what kicked off a lot of research for us into geothermal. And as we go past EGS, you can look at how our geothermal portfolio has expanded. And we have a very robust portfolio. We do a lot of things from decision support tools that are web-based to materials like self-healing cement and fracking fluid. We do a lot of technical assistance. This is both regional for resource characterization, as well as a lot for the Department of Defense and building conversion. We also do a lot in the subsurface, looking at energy storage and rock mechanics, geophysics, and geology. We have projects that are both at Newberry Demonstration Site in Oregon for Superhot, as well as Utah Forge. And we also do a lot in permitting. One of the things that we're really known for is actually our expertise at the surface with transmission planning and grid integration. And this is something that we bring in geothermal as well. So we do a lot in the surface, but we underpin that by distinguishing subsurface capabilities. And from this, we're really able to build out with our collaborators to be able to really address the different challenges that we have in geothermal, from surface to subsurface and how we integrate across that interface, enhancing exploration and development. So really, how do we find the resources and maximize the data that we have? Into economic viability, how are we going to predict that resource potential? And then thinking about how you're going to use that energy potential and transmit those electrons and then divide and then provide decision support for that. And I think with that, I will hand it over to the researchers.
Hey, good morning, everybody. Thank you so much for that overview, Jana. I really appreciate it. And thank you to GR for giving us an opportunity to come and talk to you today. My name is Hunter Knox. I'm a seismologist at PNNL. And today I'm going to give you a talk that Parker Sprinkle actually had planned on giving. This was part of work he did with Kaushik Pradhan and Julian Chaput, who are both at UTEP. So we're going to talk a little bit today about characterizing hydraulic fractures with seismic coda waves. Before I begin on the technical part of our conversation, I'd like to start by taking a minute to highlight the support that we received for this research. The funding was supplied by the NSF GTO internship program, and additionally, PNNL and UTEP provided support for the graduate student Kaushik. Kaushik is a PhD student funded through NSF grants at UTEP, and Pacific Northwest National Laboratory was able to host him as a visiting researcher this summer where we did most of this research. Also, this is an opportunity to thank EGS Collab. You can see all the partners that were part of that fantastic project. This project would not have been possible without the data and reports that were made publicly available. And it's just really awesome that we have the opportunity to utilize those efforts. And I'll just say, without the confluence of this kind of support, you're going to see a really low technical readiness level idea. These things are hard to get funded, but when you bring these kinds of efforts together, it allows us to undertake these fundamental R&D efforts. So we'd really like to start by extending our gratitude. So one of the things that we know inherently is that characterizing fractures is difficult, even in the best case, and it's even harder in hard rock. And so we start with this need of, are there ways that we can begin to understand deep fracture networks as they're being developed and as the geothermal resource is being produced? And what can we build on that we have today? So our current tools and techniques for imaging, like acoustic wellbore imaging or microseismic or ERT, and how can we build on that and improve their resolving power? So we started with the research question. Can we use coda waves to provide additional information that helps us understand fracture network geometry and its evolution? And this is a very small effort. And so we're just going to start with some very simple first steps. We're going to develop an inversion approach and a synthetic data set and see what we can learn about two kinds of inversions that help us highlight whether this can be a useful tool for EGS. And then we're going to apply those algorithms to EGS Collab May 2018 stimulation data. So for those of you who are familiar with EGS Collab, you know that it occurred inside the Sanford Underground Research Facility. That is shown on the right-hand side. The first experiment was conducted on the 4850 level. That's 4,850 feet below the surface. And you can see a basic layout in the bottom illustration. The May 28 stimulation we'll go into a little bit more, but it is basically a hydraulic fracture propagated between a stimulation and a production well. So since coda waves, like everybody understands PNS waves for the most part, we get earthquake magnitudes. Coda waves is a little bit of a smaller community inside the seismic discipline. So let's just talk a little bit about what a coda wave is. So the coda wave, as you see here on the left figure, is the low amplitude tail of the seismogram. And it represents multiply scattered seismic waves that follow our ballistic waves. So those are our PNS waves. And it's really appears as this like long reverberation after most of the data that we typically use has passed. So what is coda wave interferometry? It's actually a non-destructive testing technique that takes those waves and tries to quantify how the medium changes. And that, in our case, could be velocity variations, or it could be the movement of scatterers and sources. Fractures are fantastic scatterers. So this is potentially a very good tool to use to image them and their evolution through time. And you can see kind of how complex the scattering regimes get by going from a single scatterer, which produces a pretty simple waveform, to intermediate multiple scattering, to what we would call a diffuse field, shown in regime 3, and it produces a much more complex coda wave train. Okay, so this is a pretty mathy slide. So we're going to just focus at a really high level. There are two inversion approaches shown on this slide. On the left, we describe a linear inversion approach that we chose to test. And since coda wave energy can be approximated as energy transport, then it can be modeled as a diffusion model. These models are highly sensitive to scattering environments, which makes them prime for hard rock and fractures. In this example, we set up the problem using the linear relationship established by LaRose et al. In 2010. You'll see that in equation 1. DC is the decorrelation, sigma is the scattering cross-sectional density, and K is the kernel through which we're imaging. When we apply a least squares approach and apply a priori regularization, we can solve for the scattering cross-sectional density in equation 3. So we're solving for sigma, and that's really where it's going to tell us how our scatterers are evolving over the course of time. On the right-hand side, you'll see a little bit more complex workflow. So this is a parametric nonlinear workflow. This approach uses a genetic algorithm to optimize fracture plane orientation, position, length, and aperture. We chose a genetic algorithm because they are characteristically known for their robustness in exploring complex multimodal search spaces, and because they're capable of handling various constraints. So they're flexible, they're adaptable, and they're not sensitive to local minima, which is a great thing when you have a complex heterogeneous environment. So this is a good tool for imaging an engineered fracture system. We just note here, and there's a publication that you guys can go back and refer to if you want to learn more about these inversion approaches, but we could have chosen other nonlinear optimizations like self-annealing, but we have chosen to leave that for future research. So let's talk a little bit about the May 2018 experiment. The stimulation took place over several days, and you can see that in the figure on the right-hand side. The goal of this stimulation was to gradually grow a fracture between the injection and production well in EGS Collab testbed 1. The distance between those two boreholes is about 10 meters. During the stimulation, a variety of geophysical approaches were used to monitor the fracture growth, and detailed observations were made both during the driving of the fracture and the stress relaxation of the system. The team recorded during this stimulation about 600 microseismic events, and they're very, very small. We estimate magnitude -2 or less, and their frequency range is in the kilohertz. During the stimulation, we used Lawrence Berkeley National Lab's Continuous Active Source Seismic Monitoring System, better known as CASM, and it uses a multiplexer to acquire active source seismic data in a time-lapse acquisition. That's done by activating piezoelectric crystals and recording seismic imaging data sets, and in our case, it's done every 15 minutes. Turns out this is a perfect data set to test our hypothesis about whether coda waves are good at monitoring fracture generation and fracture evolution over time. Okay, so let's talk at a very high level about what we learned. So we had the very simple linear inversion. And we find that this relatively straightforward inversion approach works pretty well, and it's computationally efficient. The drawback in our case is that it assumes a degree of smoothness that doesn't really capture the complex heterogeneity in the subsurface and can't really resolve what we suspect the engineered structure looks like. But it is computationally efficient. So if you want an edge tool, you might choose a linear inversion algorithm that could be run in real time to complement your microseismic analysis. Next, we'll talk a little bit about the parametric plane synthetic nonlinear inversion approach. And as you might suspect, and based on our earlier conversation on genetic algorithms, the parametric nonlinear workflow allowed for clearer images in the subsurface. Remember, we were trying to optimize fracture plane, orientation, position, length, and aperture. And in figure C, you'll show the recovered plane model under the presence of a strong measurement noise. And it indicates that our plane tilt and orientation are well recovered in the inversion, but our rotation and truncation are somewhat less well recovered. We have ideas about how to overcome the weaknesses in this approach, and they look something like maybe trying to apply a Bayesian approach or another type of statistical inversion on top of this to study the trade-offs. So our initial findings in future work. We have been able to show that coda wave interferometry can capture subtle variations in fractured media that microseismic clouds may not be able to recover. Remember that microseismic locations can often be plagued by errors related to either overlapping seismic events or errors in the velocity model. We have shown that radiative transfer offers a robust framework for modeling the coda wave envelope in a scattered media. So in hard rock with fractures, this is a good approach for scientists to take in imaging fractures. We also showed that when the mean free path is small, that means that the mean free path is really the distance over which a wave field becomes diffuse. So it means it's been scattered many, many, many times. And that happens more easily at high frequencies or in very, very hard rocks or at very small scale. The radiative transfer framework simplifies to a linear diffusion equation. And this allows for computational efficiency without sacrificing too much accuracy. So this might be a very good approach to use in the field in real time for feedback. We have shown with synthetics that using a nonlinear parametric plane inversion can constrain the heterogeneity in the medium way more than a standard linear least squares approach can. So it makes it a good approach for downstream processing if you need a better understanding of the evolution in the subsurface. So this was a pretty small effort undertaken by UTEP and PNNL. Our future work, really the next things to do are to apply it to real world data, to take the chasm data and start making measurements. We have done sort of very entry-level evaluation of the raw data, and we can see changes in the correlations in the coda waves. So we know there's information there related to the fracture generation. We also have the 600 microseismic events that were generated during the stimulation. And those events, we can use their locations and their coda waves to help further elucidate what the fracture system looks like. So we can do some joint validation, both by comparing it to the traditional microseismic monitoring, and also we can combine the efforts and really look at how both active source and passively recorded seismic data can inform our understanding of the subsurface. And finally, ideally, you develop an approach for full-scale near real-time monitoring. And that could look something like we apply the radiative transfer framework to, with some supercomputing power, and that gets you to something that's near real time. I'll just say this, coda waves offer a lot of opportunity in the world. Seismic data can be sometimes very challenging and time-consuming to evaluate. Coda waves can be automated. The evaluation of coda waves can be automated in a way that picking algorithms still today have not produced good picks. So I think I'll end it with there, and I'll say thank you. There's the DOI for the leading edge article that Kaushik wrote, and I'll happily answer questions during the Q&A. Thank you.
Great. Thanks, Hunter. Appreciate that. Our next presenter is Jason Ho, the Chief Data Scientist for PNNL. Unfortunately, Jason is having a medical procedure performed this morning and is unable to join us. However, he was kind enough to record his presentation, so we'll play that now and do our best to send some healing energy his way.
Good morning and good afternoon, everyone. My name is Jason Ho, Chief Data Scientist. Where geothermal potential exists, but the surface indicators are limited. I'll start with the study size and data, then move to the joint inversion and some of our results, then discuss multimodal machine learning and what that reveals, and finally close with a summary. We targeted 3 regions: the northwest, the lower east rift zone, and Kilauea. The datasets we assembled are diverse and complementary. We have well logs of resistivity, temperature, P wave, and S wave velocity. seismic monitoring from earthquake stations, gravity data from ground station, electromagnetic data, including magnetofluidics, MT, and audio MT. Also, we drew from the 2009 USGS Open File Report as a baseline reference. Here are examples of well-known data, including resistivity and temperature profiles and physics information, and gravity station locations. So together, these sources give us both measured signals and indirect constraints on subsurface conditions. But as you might guess, no single dataset can fully describe the system. That's where our integrated approaches come in. Our approach combines two complementary tools. The joint inversion is a physics-driven method, integrating MT, AMT, gravity, seismic, and resistivity. This reduces non-uniqueness and provides geologically realistic results. Well, multimodal machine learning is a data-driven method that fuses heterogeneous geophysical modalities, learns correlations without requiring explicit forward models. These two approaches work together in a way that joint inversion enforces the physical consistency and multimodal machine learning captures the hidden correlations. We implemented a Bayesian Markov chain Monte Carlo stochastic inversion instead of one best model. This produces posterior distributions, giving quantified uncertainty. We explored several sampling strategies: multiplies, Hastings, GIPS, delayed rejection adaptive multiplies, differential evolution adaptive multiplies, and so on. These allow us to compare and identify the most effective way to capture global minima rather than local traps and adapt proposals on the fly. Advantages of this approach over deterministic inversion approaches include quantified uncertainty with posterior distributions, guidance on optimal inversion setup with bounds violation check, and captured global minima instead of local minima. This makes the inversion both robust and informative and comes with confidence intervals along with our estimates. However, I want to mention that joint inversion is not always a must to all geophysical data. For instance, if a forward model is much faster compared to others, or if there are too many unknowns, or the physical models do not share common unknowns, we don't force the integration of joint inversion. Therefore, the inversion results can be obtained via joint inversion or individual inversion based on careful comparison, selection, and integration. With that, I'm showing one result to be an extended resistivity map down to 40 kilometer depth across the central region near Mauna Kea. Here, warm colors represent resistive material, cool colors conductive. The other is a shallow subsurface section. What's striking is the appearance of conductive zones, as shown in blue, around 500 meters elevation. These anomalies are interpreted as potential fluid pathways or drilling targets. By comparing the extended resistivity maps with known volcanic structures, we were able to highlight zones of interest that align well with the historical eruptions or maybe potential production. That's the joint inversion can provide a physics-grounded and uncertainty-aware map of subsurface conditions. Now we turn to the multimodal machine learning workflow. This has three phases. Feature selection uses meta heuristics like a genetic algorithm combined with wrappers such as backpropagation, k-nearest neighbors, and naive Bayes. Feature prediction then employs modified self-organizing maps to interpolate and infer missing features. Then feature clustering applies the k-means with metrics like the Davis-Bode index to identify the coherent subsurface patterns. The features we fed into this framework include field measurements, geophysical inversion outputs, and geological constraints. Importantly, we assimilated both numeric and categorical data, then projected them into a unified embedding space. This slide highlights constraints such as state variables, head, temperature, chloride, and informative features such as geology, physical and aqueous properties, aqueous chemistry, and so on. The measured and derived parameters collectively guide our learning heuristics to help us identify subsurface geothermal signatures and fluid system characteristics. One output is a set of predicted permeability maps, essentially a permeability analog. These highlighted zones are where subsurface fluids are likely to flow. Another result is predicted 3D geological layering, where categorical velocity constraints allowed us to reconstruct likely stratigraphy. These outputs can reveal hidden geothermal fingerprints, deep permeability zones, the potential caprock layers, and likely upflow paths. Taken together, the machine learning results really complement the joint inversion maps by identifying statistical correlations that are not easily captured in physics-driven methods. As a summary, the joint inversion delivered physics-driven models with quantified uncertainty. Multimodal machine learning provided property map and 3D layering from fused data. And together, they reduce risk and help sharpen the image, the picture of the site's geothermal potential. And the next steps would include expanding to include generative AI approaches, improving resolution, and refining machine learning predictions. We also plan to have data sharing frameworks for broader collaboration. With that, thank you, and I look forward to your questions and more discussion.
Okay, that was great of Jason to record that for us. Appreciate that. And our next presenter is Nicole Harvey. Nicole is a mechanical engineer in the Building Systems Group at Pacific Northwest National Lab, where she has worked since 2022. In her time at the lab, Nicole has contributed to projects evaluating feasibility of both ground source heat pumps and geothermal electric technologies across the Department of Defense enterprise and the commercial sector.
Thanks for the introduction, Brian, and hello to everyone here. I am on the wrong slide, so let me get back to the beginning. So today, my presentation is going to be a little different than the description that was sent out. Unfortunately, I had a little bit of difficulty in getting approvals from the Department of Defense to present some of the work that I have done, which is not terribly surprising. That's a little bit of a difficult process sometimes. So today, instead, I'm going to focus on some of the work that Pacific Northwest National Lab has done around geothermal for federal facilities. PNNL works really closely with a lot of federal organizations, especially the Department of Defense. Specifically, we do a lot of work with the Army, but have also worked with the Navy and the Air Force as well. So some of the projects that I just wanted to highlight and touch on today, One project is called FedGeo. So this is a project where PNNL, along with several other national laboratories, are providing technical assistance to federal partners. There is some publications and some information on these projects published by GTO. I think the first project was done at the West Point Naval or Military Academy, and then they also did a project at Detroit Arsenal, which I believe is in Michigan, looking at the feasibility of installing geothermal for heating and cooling at those locations. So that has been an ongoing project that PNNL has been working on. The PI on that project is Tim Yoder. It's a really exciting project that I'm pretty sure is still ongoing, and it's been really interesting to talk with Tim to hear about the results from that project. So another project that I guess two projects that I was the lead on is GSA has a program called Technology Proving Grounds, and they essentially look at installing technologies in different GSA buildings to help bring them to commercial viability. And for this particular project, we developed a draft measurement and verification plan to the General Service Administration, that's GSA, for the installation and performance of ground source heat pumps in various GSA buildings. Unfortunately, we were not able to get past the draft stage for this because funds were no longer available to install the system. But it had a lot of promise. I think was going to be a really interesting project. And then for the Department of Defense, we provided some training earlier this year to various personnel, which talked about resilience benefits of ground source heat pumps for Department of Defense specific applications, lessons learned, and design and operations and maintenance considerations. This was really interesting because the Department of Defense is obviously different than just your everyday commercial building, and there was some really unique topics that we talked about in that training. Specifically, we focused pretty heavily on resilience, which is important, especially to the Department of Defense. So one of their big considerations is being able to maintain operations of their facilities, even throughout a grid utility outage event. And so we really highlighted on how efficient ground source heat pumps can be. And if there is on-site generation assets, that those ground source heat pumps can still provide heating and cooling for the Army, and they can see some pretty significant savings in comparison to other systems. So that was a fun training to give. And then we also have published various white papers and reports and articles on the benefits of ground source heat pumps, specifically at federal facilities. That top one there, we partnered with Oak Ridge National Lab to publish an analysis of ground source heat pump ECMs. ECMs are energy conservation measures. So we evaluated energy conservation measures specific to ground source heat pumps that had been installed at federal facilities through ESPC or UESC programs through the Department of Energy. And from this data, PNNL and ORNL were able to publish installation costs per ton. So, and this was also, I think this was published this year. So this is updated and very current data, which I have found useful in various other projects. There's also average energy savings that was seen per year and average annual cost savings as well associated with those installations. So if anyone is curious, you can reach out to Brian and I'd be really happy to send the links for these different reports. We also published some information on procurement options for low temperature geothermal technologies at federal facilities. This is just kind of meant to provide a high level overview of different procurement options and how you would fund some installation of low temperature geothermal technologies. It was mainly focused on ground source heat pumps, but I believe they looked at this for direct use as well. And then last but not least, kind of along the same lines, there was a white paper published on federal tax incentives for low temperature geothermal technologies. So this was looking at tax incentives that were available specifically to federal facilities to help them get these ground source heat pump systems installed. Because one of the major barriers that we see when we are trying to get installation of ground source heat pumps at federal facilities is getting them funded, and also some of those high upfront costs. So these last two papers were really helpful in providing information on that. We also have done some work in the high temperature space for federal facilities. This last one isn't as specific to federal facilities, but the first one, this multi-criterion decision-making tool is. So we developed what we ended up calling the multi-criterion decision-making tool and provided it to the Department of Defense in order to assist with site selection and prioritization for on-site installation. Again, resilience is really a big component for the Department of Defense. It's something that they focus on very heavily, something that's very important to them. And so in line with energy resilience, they were very interested in citing specific energy generation technologies within the fence line on site. And one of those technologies that they were interested in was geothermal electric. And so for this tool, we specifically looked at enhanced geothermal systems along with hydrothermal systems and talked with various Department of Defense sponsors and others to develop a list of criteria that we thought were important for Department of Defense as well as important for siting of an enhanced geothermal or hydrothermal system. And then that tool was used to identify the top sites based on different groupings of scenarios. And that tool was provided to the Department of Defense to help them moving forward in their site selection process and prioritizing which sites may be the best fit for installing these geothermal electricity generation technologies. And then this last project that I wanted to touch on in the high temperature space is for the Industrial Technologies Office. We developed 2 fact sheets, one on geothermal electricity for manufacturing partners, and then the other for direct use geothermal heat, also for manufacturing. So these are just, I think, 5-page fact sheets giving a high-level overview of the technologies and how they can be applied to manufacturing. And then I just wanted to mention too, before we're done here, this list is certainly not exhaustive of all the projects we've done for federal facilities in the geothermal space, but just wanted to highlight a couple that I was familiar with and that we're currently working on. So that's all I have for today, but thank you all for your time.
Great. Thank you, Nicole. We can go on to our Q&A session now. And so anyone who wants to add a question into the Q&A, please do so. I have a few questions of my own that I'm going to start out with here. Hunter, in your discussion of future work, you mentioned applying real-world data. Are there any studies underway with that you can share with us?
We have a couple of data sets targeted that we might try. EGS Collab has the chasm data, so that seems like a very easy next step. And so that might be some, intermediate scale fundamental R&D data that could be applied. But there's been some stimulations at Utah Forge that could be applied, and also at Newberry. We're, as I think many of us, seeking funding to continue on.
Right.
But I think there's a lot of promise in it. So you kind of have to take these tools and shake them out in real world data and figure out what the pros and cons are. So
sounds good. Thanks. And Nicole, you just mentioned the multi-criterion decision-making tool. Can you share what some of the specific criterion that are considered in that are?
I can give a very high level. I can't get into detail on it, unfortunately.
I was just about to qualify that question by saying I understand that there are probably things you can't talk about.
Yeah, but I can give a very high level that we talked about some what we called mission specific to Department of Defense. We looked at economics was a big factor, like energy unit cost. And then for the geothermal aspect of it, we were looking at things like proximity to known hydrothermal resources, temperatures at, I think we looked at 3.5 and 5.5 kilometers depth using the Stanford, sorry, not the Stanford, the Southern Methodist University geothermal maps that were available. And then there's one more criteria that I'm blanking on. Oh, we also looked at some environmental factors like earthquake risks. And I think we used the the Department of Defense has an extreme weather assessment tool that we utilized for that. It used to be called DCAT. I think they changed the name on that recently though. So that's, unfortunately, I can't get into more detail than that, but that should hopefully give a high level of some of the criteria that we used.
Appreciate it. Thanks. Jana, this was a fantastic selection of research projects to share with us. Is there any other geothermal research going on at PNNL that you're excited about that you maybe want to share like a quick hits with us?
Oh, sure. Yeah, we have a lot going on, and and I wanted to select these to really go across kind of the profile that we have from, highlighting the geophysics and more the geophysics part of that, as well as the machine learning aspects that we're doing that Jason presented on, and then into the shallower temperatures in buildings that Nicole is. But yeah, we are doing some work in Newberry, some induced seismicity, looking at the geophysics and the waveforms to understand kind of what the source signatures are on that. That's one that we're pretty excited about. We're doing a lot in resource characterization, actually, locally, and working a lot with the local governments on trying to understand, in more detail what the geothermal resources are in the Pacific Northwest and what we can actually do with that. And there's a lot of momentum in the Pacific Northwest to actually make that a reality. So it's really exciting to be part of that as well.
That's great. Fantastic. We have a question here from Ross Ribick. Is the MCDMT available to license for private industry use?
I don't believe so, since that was specifically created for the Department of Defense.
Yeah, that
But
makes
good to know
sense.
there's interest
There is
in
interest, yeah.
something like that. Yeah, I can.
Definitely. And I actually, let's see, someone just messaged me a question here. Jana, how can we as members of the geothermal industry who benefit from your work best support your efforts?
Yeah, lots of ways. Call me is one, and we can have a discussion on how we can work together. Ross, who just asked the question, he and I work quite a bit together on discussing what can we do to further geothermal, not just in the Pacific Northwest, but beyond that as well. So we're always open to partnering. We are non-compete, so I refer to us often as geothermal phone a friend. So the easiest way to do that is to just get in contact with me and discuss your interests, and then we can talk about how, we can support you, is really how that goes. We're here for the community to further research.
Fantastic. And I don't see any other questions, so that is a fantastic way to end this, I would say, on that note. I want to thank all of you for coming in today and presenting. These were fantastic, and thank all of our attendees who joined us today, and thank all of our members who made it possible. So thanks, everyone, and have a fantastic rest of your day.
Thank you.
Thanks.
Thank you.